Let's talk about some new vocabulary, inflection point, and we'll define it in just a sec, but let's start analyzing this function to begin with. Where would you say the local mins and maxes are? Well, I'm not particularly trying to fool you here. I'd say there's a local min there, local max there, and a local min there, right? At 10, 20, and 30. What else can we say about what's going on there? Maybe the derivative is 0 there, or you have a horizontal tangent line. Could you also say this is a critical point? Remember the definition of critical point? So we've got 3 critical points there. Maybe one back here at 0, but we're not going to worry about that. So local mins and maxes where you have critical points, at least if there weren't saddle points. Can we say the local mins and maxes or where the original function switches from what to what, or from this to that, or vice versa? Local mins and maxes, I forgot to say this is our original function f, or where f switches, what's switching here when you get to the local min? F was decreasing and now f is increasing again. So where f switches decreasing to increasing, or vice versa. So, fairly uncontroversial. So here's the new word, an inflection point is where f switches not decreasing, increasing, but where f switches from concave up to concave down, or vice versa. So where would you say the inflection points are on this graph? Well, here the function is concave down, and then it's concave up. So somewhere around here is an inflection point. Doesn't have to be halfway between 0 and 10. It's probably kind of close to halfway the way I drew it, but it doesn't have to be exactly. Somewhere between 10 and 20, because here the function is concave up, and over here the function is concave down. So maybe somewhere around there. And then again between 20 and 30, it's concave down near 20, it's concave up near 30. It must have switched. So looks like it's actually kind of closer to 20 than 30 here. I'm going to guess it's about right there. And then over here the function is concave down, over here it was concave up. So I'm going to have another inflection point there. So that's the definition of inflection point and some example of inflection points. Let's take a look at the derivative graph. So go ahead and sketch the derivative. We'll try to keep it on the same x-axis scale. So how can we sketch the derivative here? Well, I would start at the critical points where we know the derivative is 0. So there, there, and there. And what can we say about the derivative in between? Here the derivative is all negative, here the derivative is all positive, but then back to 0. So derivative is negative until you get there, positive, but then you get back to 0. Derivative is all negative here, but then you get back to 0. Then it's positive, maybe slightly decreasing there, the way I drew that. Actually, maybe even goes back to negative. Kind of hard to tell, but we won't worry about that. So this is f prime. What can we say about, so we said the critical points of the original function are the zeros where the f prime crosses the x-axis. What can we say about the inflection points of the original function? What do those seem to correspond to, at least in my by hand drawing here? Well, this one seems to correspond to that point, right? If I kind of imagine linking those, and that is a local max of f prime, or you could see it's a critical point of f prime. This one, well, maybe my drawing wasn't so good, but we'll do it in Desmos later and it'll be better. So that's another critical point of f prime, and the same thing over here. that inflection point there gives us a horizontal tangent line there. So it looks like the inflection points, well, inflection points are where f prime switches concave up, concave down. Concave up is about f prime increasing. So when f prime was increasing and now is decreasing, the original f is switching from concave up to concave down, and it would make sense for it to do that at a local max, right? Let's think about this in terms of the second derivative. So we'll try to keep it on the same scale again. So go ahead and sketch the second derivative of f, which is the derivative of the first derivative here. What can we say there? This point is where f prime has a critical point, so f double prime has a 0 there. F double prime has a 0 here, and a 0 here. And in between here, f prime has positive slope, so f double prime will have positive values. Here f prime has negative slope, so f double prime will have negative values. And the same pattern over here. F prime has positive slope from here all the way to there, so f double prime has positive values. And remember, we had said another way of thinking about concave up is when f double prime is positive, then the function is concave up. So f double prime for a parabola, for a smiley parabola, is positive, and here the function is looking like a smiley parabola, right? For f double prime for a negative parabola is like -2, for example, for x squared, and where the function looks like a frowny parabola, the second derivative has negative values. All right, f prime has positive slopes all the way over here, so this is just going to do something like that. So this point here, f double prime is 0, which is linked to this critical point of f prime. And f double prime is 0 there. So can we say that the inflection points of the original f are where f double prime is 0? Certainly seems logical. The question is, am I leading you into a trap? So let's write that down. Can we say the inflection points of f are where f double prime equals 0? Can you come up with a counter example to that? Take a sec to think about it. Remember when we were thinking about our critical points always mins or maxes, we said, well, x cubed has a critical point at 0, but that's a saddle point, it's not a min or a max. So maybe that's a hint of what you can come up with here. Okay, so consider x to the 4th, which looks a lot like a parabola but is fairly flat at the bottom. What's f prime? 4x cubed. F double prime, 4 times 3 times x squared. What is f double prime of 0? 4 times 3 times 0 squared, which is 0. So that point right there has f double prime being 0, but is that an inflection point? Nope. F is concave up on this side, f is concave up on that side. So x equals 0 is not an inflection point. You might say it's kind of a candidate inflection point, and then we investigated it further by looking at the whole shape of the function and found it's not an inflection point. So we could say f double prime being 0 gives candidate inflection points. And then you have to go check them. The same way that f prime being 0 gives critical points, which are candidate mins and maxes, but you have to go check them.